Hello and welcome back. In this lesson, before we jump into looking at how on Perceptron trains, that is how we find the best decision boundary by updating the values in the weight matrix, we are going to focus on vectors. And if you already know how vectors work, how to think about a dot product, you could skip this video. If you are new to vectors or have some doubts about how to think about dot products, then this video is for you. What we are going to do is first think about vectors. So when we look at any data point such as this one, which is in a two-dimensional plane, let's say uh, we have x and y axis, for example. So in that case, let's say this is our x-axis and this is our y-axis. When we think about any data point, what we want to think about is an arrow that starts from, in this case, origin and goes all the way up to the point right here. And this arrow is what we call as a vector. And vector, when we say this is a vector, what we are going to think about are two things. First one is the direction, and this is very important, because when we say that we have two sets of data points on this side and this side, what we are essentially saying is that the arrows or vectors in this particular side are more aligned in the same direction as compared to the arrows that are on the other cluster, which are sort of aligned in a different direction, but in the same cluster they are sort of pointing in the same direction. That's what we are getting at. So these arrows uh, on this side, let me get the pen. So these arrows on this side, they are sort of pointing in this direction and general direction. These arrows are pointing in this direction. So vector gets us a direction, and we can count, or we can measure, or we can get a calculator. We can calculate direction, right? We can calculate the direction. You can get the angle, and that tells us where to separate these data points, right? That's where we will get at in the next video, but here we are just going to think about vectors. So that's our data point right here, and this is a vector. So one thing we said, that the vector gives us a direction, and that this is sort of the reason why we need the direction. The second one is magnitude, and magnitude is essentially the length of the vector. So uh, l- how long the vector is. So that again is important, because if we have if we have data points that are uh, of different scales, different magnitudes. For example, let's say we again have this x and y axis, and here we have couple of data points. Now, some data points are pretty small. They are, let's say, these are the three data points. They're pretty small. They are right here. And then we have a couple of data points that are very large in magnitude, that are maybe somewhere here. These are three. And let's imagine that this x-axis, this y-axis is, uh, we are not showing the entire scale of the y-axis. So we say this is broken, and here this value is 1, and let's say here this value is 100,000, right? In this case, what happens is, if we start thinking about our data points, if we say that, well, this is one arrow, this is one vector, this is another vector, that's the third vector. Now they are very small in magnitude, very tiny arrows, and then we have these other set of arrows or vectors, which are fairly uh, large as compared to our original small arrows. So these are pretty large arrows, as you can see these. And so again, when we take a dot product, uh, when we are trying to um, uh, get the dot product to find the optimal W, what happens is these large arrows that we have, they tend to dominate. So they tend to dominate the calculus. So these will dominate the values of the dot product just because they have a large length, right? So what we do then is we normalize these and make them both of these set of vectors same length, so that we can compare just the direction by itself to separate out that this is a different group as compared to this is a different group of data points, right? So that's why we need to have a measure for direction, measure for magnitude, and that's why vectors are so important and so helpful. So uh, this is then the one sort of reason why we need vectors. Now vectors are not attached to any one location. That is again something that we need to think about. For example, here I've drawn a vector which is at say point 0 0. This is, let's say, 1 1. This vector is not attached to that particular origin 0 0. We could take this vector and draw it here, right? And it would still be the same vector. It would still be the same vector. Why? Because it still has the same magnitude, it still has the same direction. And that is the whole story about vectors. If I now take this x-axis and sort of draw on this side, let's say negative side, we can draw this arrow, and let's say here we are, this was 1 2 3, so that was where we were at 1, and I'm going to move this little to this side. So let's say we are here and this is now at -1. If we say this is -1, right, and this is now, this is still 1, but then we are at x is 0 and y is 1. This is a point where we have x is -1, y is 0. Both of them are the same vectors, they have the same direction, they have the same magnitude despite they having the different locations. So point to note from uh, here, when we are where we are talking about what is a vector is we can think about it as an arrow pointing in space, just as we see here the blue arrow, which has, which gives us information of the direction, and that, as we saw here, it can help us separate out or classify data points. Then it gives us magnitude, that again helps us sort of in scaling the data points that we have, right? So if we so that's, and we'll get into more detail how that affects later on in the series. But for now, I hope this gives you a clear idea of what a vector is. And vectors are not anchored to one location. Anchored to one location. Okay. So these are the points I'd like you to remember. The next point we can look at is the dot product and how we measure the alignment. So to write that down here, dot product. So you probably already know what a dot product is. If we have uh, let's say a vector, horizontal vector 1 1 like this, and then we have another vector 1 1 like this, and we try and do a dot product, what we are trying to do here is to make things stand out, and we are going to change these to different values. What we essentially do is take these values, multiply with these values and sum them up. So the way we do that is take this 1, multiply it with 3, and then plus take this 2, multiply it with 4, 2 times 4, and so what we get in the output is 3 plus, so that is 3 plus 8, and uh, that gives us a value of 11. So the dot product here is 11, and this value is positive, right? So a positive value, and that's a large number. We if we compare that to another set of data points, where let's say we have the same the 1 1, but then the other vector that we have is -3 -4, and if we now try and take the dot product, what we need to do is multiply the one with -3, then we need to multiply the second one with -4, and then we sum these values up. So what we get here in the output, oh, looks like I made a mistake, so this needs to be 2, so that becomes 2 times -4, that's 1 times 3. So this gets us -8, and this adds up to -11, right? So if we try to plot these points, now this is the same magnitude at this one, so both vectors are of the same size, but look what happened here. We get a negative sign. What that negative sign tells us is that this vector -3 -4 is not in the same direction as the 1 2, uh, but the 3 4 was in the same direction as 1 2, and we can try to plot that. So I'm here in Desmos, and if we try and create a plot where we say vector, and we start, let's say we start both the vectors at origin, and the first vector we can draw is 1 1, which is the which is what we are comparing with. So that's our vector 1 1. Let's change this to 2D, and then we create another vector below that, which is sorry, let's make this 1 2, because that's what we calculated. And then we have this vector, which again starts at 0 0, but then the head is at 3 4, right? So here we can see that it is not exactly in the same direction as the red arrow, but it is in the similar direction as compared to this case where we have another vector again starts at the origin, but then this is pointing in -3 -4 direction. And what that tells us is we can clearly see that the green vector is pointing in completely different direction as the red arrow. And in when we try and train perceptrons, our entire goal then is to have, like, if we have, this was what we said we had the, and then we had the another, let me use the same color, so we have the, so the entire goal here is that we find an w and values for w that gets us to this ideal value, which is the shown here by the red arrow, and that's sort of the goal, and dot products help us get there. So point to note in this particular part is that the dot product helps us get a sense of direction as well as magnitude. So here both of them are of the same magnitude, but then the directions are a little different. Now let's think about this little more. If we have a couple of vectors, and let's say we have these vectors, where we have this red arrow which is pointing from origin, which is 0 0 to 1 1. Then we have other set of arrows, and as you can see that as we move from this particular blue arrow or to green to violet to red, we are pointing in the same more and more in the same direction as the red arrow. And imagine that the red arrow is the ideal W that we would like to find when training a perceptron. And the process of moving this arrow from blue to red to violet is the training process, where we are updating the weights W to find the appropriate values for W. Why do we do that? Because then that helps us get the decision boundary, which we saw previously, that it is uh, perpendicular to uh, the weight vector. So if that is the weight vector we have, then the decision boundary is going to be perpendicular to this, maybe something like this one, and that can help us classify data points like so. And we'll see examples of this. So before we get there, let's first think a little bit more about the dot products. And in this case, what we have are these data points. If we try and now calculate the dot product between this 1 1, which is shown here in red, which is 1 1, and let's say the blue arrow, which is shown here by the data point 2 and then comma square root of 2. All these arrows are of the same length, and that's why we have these weird uh, coordinates, square root of 2, but that is just to create these arrows of the same length. And why we need them of the same length? So that uh, we are looking at similarity based on dot product. If we have different magnitudes or different length of vectors, when we do a dot product, we are going to get that magnitude effect in there. So a larger, if you are multiplying a smaller arrow with larger arrow, then the dot product would be larger. If they are all of the same length, then we can compare very easily to get sense of direction. And here is what we have. This function is just calculating the dot product, and this is the point 1 1, and then we have this point, which is 0 square root of 2, 0 square root of 2, which is this blue arrow. And when we try and calculate the angle, it is 45 degrees. So here we can see that red arrow and this blue arrow, they looks like they are at 45 degrees to each other. Now let's try and calculate. Let's say we did one iteration of the neural network and training, and we came to this new arrow, which is the green arrow, and now the coordinates are 0 0.5, 1 point, square root of 1.75. So if we take 0 0.5 square root of 1.75 and try and find the angle between those two, wow, so we are getting closer to the say closer to 0. That is to say, we are getting closer to the red arrow, and here the angle is now 24.3. So we are now moving closer to the red arrow. And now let's say we update our W further, and we happen to get to this particular vector, where which is the violet vector, where we have the coordinates 0.75 and square root of 1.25. So if we see, look at 0.75 and square root of 1.25, then the angle is just 11.15, so 11 degrees. So we in training the neural network, this is what we intend to do, is find the ideal W, and so we want to get in the direction closer to this red arrow. And here we are at 11.15, and that's pretty close to the red arrow as compared to where we started at 45 degrees. Now in ideal case, the arrow that we would be most the best arrow that we would look at, or vector we would like to find for W that gets us the best decision boundary, is the red arrow. So if we dot the red arrow with itself, which is the 1 divided and 1, and then we have 1 1 1 1, same data point. So we have two arrows which are of the uh, which are essentially the same. We try and calculate the angle between them. It is 0. Now that is 0 because they are now exactly. So we can say that we found the most ideal W that can help us find the decision boundary to separate the data points that we have. So that's how the perceptron tries to do a perceptron training. What we try to do is try to find the optimal w, um, just so that the when we move this particular uh, weight vector, along with it we also move the decision boundary. So that's the weight vector. This would be the decision boundary, and then if we change the weight vector to something like this, then the decision boundary moves along with it, perpendicular to it, something like this. And so if we had a red data point here which was previously misclassified, now it is correctly classified, because we moved the decision boundary to this side. So that is what we are thinking about um, dot products. Again, to calculate the cosine, this is what we said. We use the dot product of one vector with another vector and then divide it or normalize it with the magnitude, which is this one. So a dot b, then divided by the magnitude. So I could just write it this way. We have a dot b, like so. All right. So so far what we looked at is uh, what are vectors, what is a dot product, and how the cosine can help us find that particular vector. Now let's look at yet another example. What we have here is a set of vectors all pointing in different directions, and what we are going to think about is how well they align with the red arrow in this case, which is this one. That's and these are all the arrows we have. So if we start plotting each one of them, now this one is perfectly aligned with the red arrow that we have, and that is what we want. So if we have a weight matrix which is pointing in this direction, which means our decision boundary is going like this, and maybe that's the ideal decision boundary that we would like to get to. And so this blue vector sort of will do that job for us. Now if we look at other directions, which is this one, now the green arrow, it is pointing in similar direction as the red arrow, but it is not quite as aligned as the blue arrow is. Blue arrow is essentially exactly the same direction. Green arrow is in the similar direction, but not it's there's still room for improvement. Now if you look at the violet arrow, it is in completely different direction as compared to the red arrow. And so it's or if we have weight matrix that is that far off from the ideal values, then is likely going to create a decision boundary that is going to misclassify a lot of data points. And so we definitely have to update the values in that weight matrix to get it closer in the direction as the red arrow. And likewise, if we have another uh, arrow that we see here in gray, again not in the same direction as the red arrow, but looks like it's still better off as compared to the violet arrow, which was exactly in the opposite direction. If we try and take these arrows and put them here, uh, I'd like to show you how the dot products would come into picture here, with where the shapes are different. Previously we looked at all the vectors where all the shapes were the same. Here we have this arrow which is 2, x-axis 2, y-axis 1. Then we have the second arrow right here, where we have the x-axis is 4, y-axis is 2. Then we have the green arrow. The green arrow has coordinates 2 comma 3, and then we have the violet arrow, which again is uh, pointing in completely different direction, which has a coordinate of -2 for x and -1 for y. And finally we have the gray arrow, which is in the direction plus 1 for x and minus 2 for y. If we now try to get the dot products of these, let's see what happens if we take the dot products without normalizing the data points. So what we are uh, focusing right now is dot product, as we have seen previously, but then we are also going to think about how to normalize and why we need to normalize the values before we do any sort of dot product when we are trying to uh, get a sense for direction. So when we talk about normalize, what we are saying is that we take whatever vector we have, let's say value 2, 3, then we divide 2 by the length of that vector, then we divide 3 by length of that vector, and that's sort of the normalized value for that vector. And normally, let's say we had another vector here. If we had to draw one, let's say we had another vector here that goes somewhere like this, right up to there. That's at let's say point x-axis 1, y-axis 5. Right? Now, if what we have been saying is that if the dot product is larger, then that particular data point is similar to the other data point, or that vector A is similar to vector B. A is similar, more like similar to vector B if the dot product is higher. But there is a problem with that if the vectors are of say a different length. For example, here we know that this vector 2 3, so let's say this is our ideal 1 2 1, and then say we have the vector 2 3. If you try and take the dot product of this, we have 2 times 2 plus 1 times 3, and that gets us 4 plus 3, that is 7. So dot product of this vector and the red, what we get is a value of 7. Right? Now what we do is, if we take the dot product of again 2 comma 1, but then we use this another vector 1 5, which is of different magnitude. It is farther away from the red arrow, but it is of larger magnitude. It's a longer arrow, as we see. Now if we take a dot product of this, we have 2 times 1 plus we have 1 times 5, and so we end up with a value which is looks like it does look longer, but then the dot product is the same, and so we get a 7. So based on just dot product, we cannot tell uh, if this particular is similar arrow is similar. If this is A, this is B, and this is RW, then we cannot say that B is closer to W as compared to A, because they are of different length, different magnitudes. And so what we need to do is we need to normalize each of these values. So for example, here if we were to try and get the length of A, it would be 1 square root of 1 square plus 5 square, that is square root of 1 plus 25 is equal to square root of 26. And so square root of 26, if I were to calculate on my calculator, it comes out to, let's see, square root of 25 square root of 26. So my mistake, 26 and not 25. So square root of 26 is 26, and we raise that to the power of this. This is 5.099, and 5.099 is the magnitude of this one. If we look at the magnitude of 2 3, we have 2 square plus 3 square, we have this is 4 plus 9, that comes out to square root of 13. And let's look at square root of 13, what it looks like. We get a value of 3.6. So 6, and therefore we see that definitely this arrow is much larger than this one, but still we get the same dot product, and what dot product, if we use this analogy, what this is telling us is that both arrows are equally similar to W, but that is not the case. We clearly see that this is much farther away from this arrow right here, right? And so that's where the normalize part comes in. What we can do is we can normalize this, as we saw here. We can divide it by the length of the vector. So let's say we have this vector 2 1, and then we have another vector 2 1, which is, let's say we are saying that we are looking at the same red arrow this time. We can get normalize it. Normalize it as the same way as we did just now. Just divide each coordinate x and y by the norm, which we did here. Take the square, add them up, take the square root, and then use the 0.5. So we do, so this normalized value for this would be 1 divided by 5.099. The y value would be 5 divided by 5.099, and same thing for this one. This would be 2 divided by 3.6, and this would be 3 divided by 3.6. And that's exactly what we are trying to do here. Is we take these values, get the normalized values, and we see that because it is the same vector, we are trying to find the direction for using the dot product. The value is 1, which is good. I mean, that's the max value we are going to get, because we are now using normalized values to perform the dot product. So dot product of normalized A and normalized B. If we take the vector 2 1 and dot it with the normalized value of 4 2, which is the same direction but a larger magnitude, as we see here, we take this value and this value. If we normalize it, we get the value of 1, which is exactly what we would expect. But if we did not normalize, then we get a higher value. That suggests that, oh, in that case, then this 4 2 is more similar to 2 1 as compared to 2 1 to 2 1 itself. That does not make sense, right? And that is because we haven't normalized. If we look at the non-normalized data, so normalizing helps. If you look at the dot product of 2 1 with 2 3, which is this green arrow right here, uh, after normalizing, we see that it is 0.86. And if we use the data point 15, we will probably get a value that is larger than 0.86, if we, or maybe similar. So if we normalize this, we get a value of 0.61, sorry, smaller value, I mean smaller value. So smaller value, it means that this vector is not similar, little less similar to 2 1 as compared to 2 3, because the dot product here is a little larger than this one. So 0.8 as compared to 0.6, and that is what helps us when we normalize the vectors if they are of different magnitudes or different lengths. If you look at now -2 -1 and 1 comma -2, this is what we get. -1 -1, completely opposite direction. That is indicated here by the negative sign. We definitely want to update that W. And if we look at 1 -2, we get a value of 0 when we perform a dot product, and that is essentially telling us that this vector 1 -2 is at 90 degrees, or is orthogonal to the vector 2 1 that we have. And that is and that so that's the again, it tells us that it is 0, which means that it again is uh, uh, it is not similar to the vector 2 1 that we have here. So that's what we are trying to see. And if we were to draw the decision boundaries for each of these, here is how they would look like. And let's try and plot the one for the 1 5 first, and we see that it will be 90 degrees. So I'm just trying to draw this. This is how it might look like. Then for the green arrow, we are talking about 90 degrees, so maybe something like this. For the ideal case, the red arrow, we are looking at 90 degrees, which might look maybe something like this. Then for the violet arrow, it might look something like this, which is going to be exactly sort of similar to this, except in the opposite direction. And then for the gray arrow, the decision boundary might look uh, something like this one. So that's the whole idea about normalizing vector or normalizing data. So the take-home message here is that if we are trying to compare vectors or data points that are of different magnitude or different scale, then we normalizing helps us to find uh, similarity between them using dot products, because then we sort of remove the effect of scale. Now let's look at another concept with vectors, which is again very important, is that vector vectors are free in space. So they could be starting from a different point, but if they have the same length and same magnitude, it's essentially the same vector. On this plot, we have 4 different vectors and they are identical. So we if we look at this vector 0 to 2 comma 1, so x-axis 2, y-axis 1, that is the same as the green vector, that is the same as the violet, and say same as the blue. And how do we know that is true? Because if we slide this vector on top of this, they are going to uh, uh, be overlapping each other. And why that is the case? Because if you look at the slope, they are in exactly they are the same inclined, all of them, they are parallel, and they have the same length. All of them have the same length. If we try to calculate the values, we here is how we can do that. So this vector, this is starting at x-axis is 1, y-axis is -1, uh, and let's use the same colors there so it's easier to read. This starts at x-axis 1, y-axis -1, and ends at x-axis 3, y-axis 0. Then the red arrow, as we see here, starts at 0 0, and this ends at 2 1. Then we have the green arrow. The green arrow starts at -1 x-axis, y-axis 0, 2 1 1 on the xy axis. And finally we have the violet arrow, which starts at x-axis 0, y-axis 2, and goes up to x-axis 2, y-axis 3. Right. So what we are saying is that all of these vectors are similar, and we can try and see how that is the case. So if we look at uh, this first one, so if we look at uh, the very first vector red arrow that starts at origin, if we uh, try to shift it to origin, what it is at origin, but let's say if we want to shift it to origin, we essentially say the following: the origin point of that arrow, which is coordinates 0 0, those are the tail, and the head part where we have this 2 1, that's the head. So we subtract the tail from the head. So here I say vector head minus vector tail. So we are essentially saying 2 minus 0, 1 minus 0, and we get a value of 2 1. So uh, that is the vector, which is essentially the same vector that we had before. Now if we take the other vector, let's say starts at the tail of -1 -1, so 1 -1, and this ends at 3 0. We change this to 3, and look at the output, we see that this has become -2, -1. That shouldn't really be the case. See, this is one. Uh, so tail, my mistake. So at the tail, it's sort of miswrote. So this is the head, and this is the tail. So this has to be 1 minus 1. My mistake. And if you look at this, it is the same vector to 1 that we saw earlier. If we take the green arrow, for example, the head is 1 1, which is right here. Let's type 1 1, and the tail is -1 0, which is this. If we look at the output, again this is the same vector to 1, which is the red arrow, and then we finally, let's look at the violet one. The head is at 2 3, and we can write that out here, 2 3, and the tail is, I think, at 0 comma 2. So 0 comma 2, and then we look at the output, it is 2 1. So points to note is, if we have a vector that is of the same length and magnitude, so vector of same length and same direction, then it is length or magnitude, then essentially they are the same vectors. And if we ever have to do a dot product between vectors such as this one, ideally what we want to do is bring such a vector to 0 and then do the dot product. So how do we and we just saw that if we have a vector such as this one, if you want to bring this tail part to 0, then what we need to do is we need to subtract the head, the tail from the head. So if we have 2 3, I'm repeating myself here, and if the tail is 0 0 and 2, what we do simply is subtract the following 2 minus 0, that gives us the x value, and then we subtract 3 minus 2, that gives us the y value. So in this case we get 2 comma 1, which is the same vector as we have here, which is the red arrow. So the final point before we end this video is that if we are trying to do a dot product, we need to have the same origin for the vectors that we are trying to dot them with. For example, here we have, because if we try to dot np dot dot, and if we are trying to dot this vector, let's say the vector a that we have is the vector we drew here, which is 2 1, and then we are trying to dot this vector with the vector b, which is the vector that we have here in the violet, which is 2 3. We try to do this dot product with the 2 3, that is not going to that's not going to get us the expected result. It's going to get us a value of 3, because we are dotting it to 3. And ideally what we should be doing is not we need to move that vector so that their origins are at the same point. So this is starting at 0 2, this is starting at 0 0. So what we want is a vector that starts at the same point. So what we need to do is subtract the tail from this. We say minus the tail is at 0 2, and now when we perform the dot product, we get a value of 5, which is the same as if we would take the dot product of 2 1 with 2 1, and the reason for that is that you already know is they are the same vectors, right? So a point to remember is, if we have to dot two dot products, if we have to get a dot product of two vectors to see how similar they are, then we need to make sure that they are starting at the same origin. And if we think about the data points that we have in the space, usually when we are training neural networks, we automatically assume that all of these data points that we see have a vector that starts at the origin. So that is sort of the basic assumption we can make when we perform these dot products. All right, so that was it for this video, and I hope that in this video you got an intuition about what is a vector, how to think about a vector. Then we looked at what is a dot product and how to think about the implications of dot product, how it moves the uh, vector closer to another vector. Let's say the ideal vector is W, uh, and we are trying to get our training progress in a direction where we are approaching that ideal W vector to get us a perfect decision boundary that we need to separate or classify the data points. Then we also looked at if we have vectors that start at a different origin. We are trying to get a dot product. We need to bring them at the same origin, which we can do by subtracting the tail from the head. And then finally, we also looked at if we have vectors that are of different length, that is, if they are of different magnitude, then using uh, just the dot product is not going to give us a clear picture how close or similar they are, because a larger vector would give a larger value for dot product. That does not necessarily mean that that vector is similar to the vector you are looking to find similarity with. So in those cases, you could calculate something like a cos theta to get the angle, or if you are using the dot product, then we definitely want to normalize the coordinates of that vector to by its length to give you sort of clear picture of the dot product, and then tell you if a particular vector is similar to another vector, or if it's completely different direction and is completely dissimilar. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope to see you all in the next video where we discuss the same concept, but then we will manually calculate the weight matrix as we train a perceptron in a 2D, and I'll also show a 3D case as well. I hope this was helpful to you. Thank you. Please like, share, and subscribe. Bye for now.